Hello students, I am Professor Sanjay Bhargav, once again welcoming you to my YouTube channel Physics with Dr. Sanjay Bhargav. To all the persons watching this video, I request you to like and subscribe my channel, press the bell icon button so that you can receive further notifications as and when videos are uploaded. In this lecture, would be talking about electric dipole, what are the properties of the electric dipole, then how to calculate electric field at an axial and an equatorial point, and then discuss how will a dipole behave when kept in a uniform electric field and non-uniform electric field. So let us begin with defining electric dipole. An electric dipole is a pair of equal and opposite charges minus q and plus q separated by a distance 2a. Now let us say this represents a charge minus q plus q and they are separated by a distance a. Then all the properties of the dipole are described in terms of a quantity called dipole moment. How do we define electric dipole moment? Electric dipole moment is defined as the product of magnitude of the charge and the distance of separation. Mathematically, dipole moment P must be equal to Q times 2A. Now, dipole moment is supposed to be a vector whose direction would always be from minus Q to plus Q charge. The unit of dipole moment is coulomb meter and the dimensions are L1, T1, ampere power 1. Now the question is, how do we speculate, how do we imagine about a point or an ideal dipole? For such a dipole, we lay down certain conditions. The first condition says the magnitude of the charge must be as large as possible. That is, Q must approach infinity. Similarly, the second condition is the distance of separation must be as small as possible. That is, dipole size 2a should approach 0. So 2a approaches 0. Now the third one is the limiting condition, which says the product P is equal to Q times 2a must always remain finite. What does this tell me? It tells me that charge Q can never become infinite. Similarly, the distance 2a can never become equal to 0. To calculate the electric field, we need to define what is dipole axis, axial point and equatorial plane. So we can imagine a straight line passing through the center of negative and positive charge would be called as the axis of a dipole, and a point of observation, that is lying on the axis of the dipole, would be called as axial point. So that is how we have written here. A line passing through center of negative and positive charge would be called as dipole axis. Similarly, a point lying on the axis of the dipole is called axial point. The third word that would be required is the equatorial plane. A point lying on a perpendicular plane to the dipole axis is called equatorial point. Or we can imagine a point of observation lying on the perpendicular axis with respect to the axial line would be called as equatorial point. Now let us imagine how to calculate electric field due to dipole at an axial point. So for that, what we do is we consider a dipole here, and the dipole has a dipole moment P in this direction and must be equal to Q times TA. This is minus Q charge, this is plus Q charge. O would be the center of the dipole, negative charge placed at point A, positive charge placed at point B. We have an axial point here which is at a distance r from the center of the dipole. Now what would be the electric field at the point P, which is at a distance r? It would be obtained by the electric field would be equal to the sum of the electric field produced by the negative charge and the positive charge at the point P. That is what we have written here. The electric field at the point P, that is at a distance r from the center of the dipole, will be obtained by adding the electric fields due to negative charge and the positive charge placed at the points A and B respectively. Now let us calculate what would be the electric field due to negative charge. For the negative charge, the distance till the point P would be equal to r plus A. Similarly, for B it would be r minus A. So here we have electric field that would be due to negative charge which was placed at A. So electric field due to charge at A would be equal to kq upon r plus A ka whole square. The direction of the electric field would be minus r cap. So negative charge has an electric field towards the charge. So that electric field is in the negative direction. So minus r cap, that is what we see here. Similarly, the electric field due to positive charge placed at point B can be calculated as kq upon r minus A ka whole square. The direction away from the positive charge, and that is was to the right. So we have the direction given by positive I. What does the superposition principle say? The total electric field must be equal to the vector sum of the two fields EA and EB. So E would be equal to EA and EB, sum of it. Substituting the values of EA and EB, what I get is EA was equal to kq upon r plus A ka whole square minus r cap plus kq upon r minus A ka whole square r cap. Just k and q are common, I can be writing it as 1 upon r minus A ka whole square minus of 1 upon r plus A ka whole square. And this simplification gives me the value kq 2r 2a upon r square minus A square ka whole square, and the net direction is r cap. And what is q into 2a called? That would be called as dipole moment. So q times 2a in the bracket here and 2r here. So the net electric field would be equal to twice kr p vector upon r square minus A square ka whole square. Now what was the condition for the point dipole or an ideal dipole? R must be very much greater than A. In that condition, r square minus A square can be replaced by simply r square. So this electric field now becomes twice k r p vector upon r power 4. 1 r cancels out, giving me twice kp upon r cube. K can also be written as 1 upon 4 pi epsilon 0 2p upon r cube. A very important thing to be noticed here is the electric field is proportional to 1 upon r cube. While in case of a single charge, it was proportional to 1 upon r square. So what does the electric field depend upon? It depends upon dipole moment of the dipole. That is, it depends upon P. It depends upon nature of medium surrounding the dipole through epsilon and the distance of point of observation, that is r. So the dipole moment of the dipole, distance of point of observation, and the nature of medium surrounding the dipole. The direction of the axial field is along the direction of the dipole moment. Dipole moment is always from negative charge to the positive charge. So the direction of the axial field also from negative charge to the positive charge. I hope there is no difficulty in calculation the electric field at an axial point. Another field that needs to be calculated is electric field due to dipole for points on the equatorial plane. So let us think about a figure here. We have the charge minus q plus q. That means we have once again selected a dipole such that the dipole moment is P is equal to q times 2a. Minus q charge placed at point A, plus q charge placed at point B. Then we choose a point of observation here P, which lies on this plane, which is perpendicular to this dipole, kept like this. So there would be an electric field produced due to negative charge at A, and that direction of the electric field would be towards the negative charge. So this direction is given this way. Similarly, due to positive charge, the direction of the electric field would be away from the positive charge. So this represents the electric field due to charge at B. Remember, we can calculate the component of the electric fields. So for EA, we have one component EA cos theta this way and another component here EA sin theta. Since this angle is theta, so I can say this angle would also be theta. So we resolve EB into two components. One would be the cos component this way, another would be the sin component this way. So we have here the same thing we have written here. The electric field at point P would be obtained by the vector addition of the electric fields produced by the minus Q and the plus Q charges placed at the points A and B respectively. Now from this figure, what we can do is we can calculate the distance AP. It's a right angle triangle. AP would be equal to BP and it would be equal to under root of R square plus A square. From this triangle, you can calculate the value of cos theta. That would be equal to base upon the hypotenuse, which is A upon under root of R square plus A square. Now what would be the electric field due to charge at B? It would be equal to KQ upon BP ka square. So it would be KQ upon R square plus A square. Similarly, I can calculate what would be the electric field due to minus Q charge placed at point A. So it would be equal to KQ upon AP ka square. So AP square can also be written as R square plus A square. What do we observe? The electric field EA and EB are equal in magnitude. So there are two components in the figure, EA sin theta and EB sin theta, which are now equal in magnitude, opposite in direction, pass through the same point and therefore cancel each other. From the figure, we can see both the cosine components are in the same direction. So what would be the net electric field? It would be equal to sum of the two cosine components. That is what we observe here. The total field at the equatorial point would be given by E is equal to EA cos theta plus EB cos theta, which is KQ upon R square plus A square. And what would be cos theta? A upon under root of R square plus A square. Similarly, we can substitute EB and cos theta here. It would be equal to KQ into 2A upon R square plus A square power 3 by 2. Now what is Q into 2A called? It would be called as the dipole moment. What is the direction of the cosine components? It is opposite to the direction of the dipole moment, and that is why we have a negative sign here. So E vector would be equal to minus Kp upon R square plus A square raised to power 3 by 2. The negative sign shows that direction of the equatorial field is opposite to the direction of dipole moment. What is the condition of the ideal dipole? R must be very much greater than A. On that condition, R square plus A square can be written as R cube, neglecting A square now. So I have the relation E is equal to minus Kp upon R cube. K can also be written as 1 upon 4 pi epsilon 0. So once again, what we observe, electric field is once again proportional to 1 upon R cube, and there is dependence on the nature of the medium. So we would like to conclude here. The dipole field at larger distances falls off not as 1 upon R square but 1 upon R cube. Whether it is axial field or the equatorial field, in both the cases the electric field decreases as 1 upon R cube. The magnitude and direction of the dipole field depends not only on the distance R but also on the angle between the vector, position vector R and the dipole moment. Because at the axial point, the axial field was in the direction of dipole moment, while the equatorial field is opposite to the direction of a dipole moment. Now let us discuss physical significance of electric dipoles. There are molecules in which the center of negative and the positive charge do not coincide, and they are basically called as polar molecules. They have permanent dipole moment. Whenever such molecules are kept in the external field, then what happens? All the dipoles are aligned in the direction of electric field. But there is another category of material in which the molecules have centers of negative and positive charge coinciding each other, and such are called as the polar non-polar molecules. Now when they are kept in an electric field, what happens? The center of positive and the negative charge separates out, and induced dipole moment is produced on the application of the electric field. So when non-polar molecules are kept, then what happens? Then the electric field has to work. First, to produce dipole moment, and secondly, to align the dipoles in the direction of electric field. Now, I can say various materials give rise to interesting properties and applications in presence and absence of electric field, because behavior of polar and non-polar molecules is different in external field. Now what we find, the total charge on the dipole is supposed to be 0. So it just makes me feel that may the electric field be 0, but really the electric field is non-zero. We have found that at the axial point, at the equatorial point, the electric field due to dipole does exist. And why? Because the charges minus q and plus q are separated by some distance, so electric field due to them do not exactly cancel out. And that is why we find resultant field on the axial point also and on the equatorial point also. A very key point to remember, the electric field due to dipole falls faster as 1 upon r cube as compared to the single charge q, where it falls as 1 upon r square. So in case of dipole, the electric field falls faster as compared to the single charge, where it falls as 1 upon r square. I hope we are very clear in determination of dipole moment, electric field due to dipole at an axial point, at an equatorial point. Now we will move forward to study how will the dipole behave when kept in a uniform electric field. At this juncture, I once again request you all to subscribe and like my channel Physics with Dr. Sanjay Bhargav. Now what is uniform electric field? An electric field which has same magnitude and direction at every point in space would be called as uniform electric field. So what would be the field lines? The field lines would be exactly parallel to each other and they would be equidistant also. So this spacing would also be same. So we say electric field lines for a uniform field are equidistant and parallel lines. Now what we do is we consider a dipole A, B placed in a uniform electric field. Then positive charge would experience a force in the direction of electric field, F1 is equal to Q times C. Similarly, the negative charge would also experience a force opposite to the direction of electric field, and it would be minus Q times C. The direction of the dipole moment would be from negative charge to the positive charge. So what does angle theta represent? Angle theta represents the angle between the dipole moment vector and the electric field. So here what we say, we consider a dipole of dipole moment P which is placed in a uniform electric field E. The two forces F1 and F2 are equal in magnitude, opposite in direction, and do not have same line of action. This produces a couple of forces which generates a torque. So in this case what is happening? Both the forces are equal in magnitude, opposite in direction, and therefore the net force acting on the dipole F is equal to F1 plus F2 would be equal to 0. If the net force is 0, then I can say no linear motion of the dipole will be possible. But F1 and F2 are equal in magnitude, opposite in direction, but do not have the same line of action, and therefore they do not cancel each other's effect. They act like a couple of force to produce a torque. What is the value of the torque given by? Magnitude of the force into perpendicular distance between the forces. Now just what is the perpendicular distance here? The perpendicular distance between the forces would be given by BC, and BC can always be calculated by the geometry of this figure. That's what we are doing here. So torque would be equal to force, and that is Q times C, and the perpendicular distance is BC. Now we have a triangle ABC. I can calculate sine theta. It would be equal to BC upon AB, or BC would be equal to AB sine theta. AB is nothing but 2A, that is the length of the dipole. So I can substitute the value of BC here as 2A sine theta. What would be Q times 2A equal to? That would be called as P. So this can be written as, tau can be written as P cross E. And what does theta represent? It is the angle between the dipole moment vector and the electric field. The direction of the torque is perpendicular to the plane of the paper and inwards. One can always calculate the direction of the torque by the right hand thumb rule. Torque is an axial vector, so always calculate the direction with the help of right hand thumb rule. In uniform electric field, what do we observe? The net force on the dipole is zero. So linear motion of the dipole is not possible. Net torque is non-zero, so rotational motion of the dipole takes place. What does the torque do? It tends to align the dipole parallel to the direction of electric field. When P is aligned in the direction of E, then torque necessarily becomes zero. So that is something called stable equilibrium. So we have the two situations here. Theta is equal to 0. Again torque is minimum. So how do we imagine the figure? This is minus Q charge, this is plus Q charge. This would be the direction of dipole moment, and this is the direction of electric field. In this case, force is 0, torque is 0, and therefore they are said to be in stable equilibrium. Theta is pi, sine 180 would be 0, so torque is once again minimum. So here force is 0, torque is 0, but the direction of the dipole moment is opposite to the direction of electric field, unstable equilibrium. So when the dipole is placed parallel or anti-parallel to the field, it experiences minimum torque. So these are the two positions in which the dipole would be experiencing a minimum torque. When theta is 90, torque would be maximum, P times E. So how does it look like? Positive charge would experience a force to the right in the direction of field. Negative charge would be experiencing a force to the left opposite to the direction of electric field. And in this case, it would experience a maximum torque. Now the question is, what happens when the dipole is placed in a non-uniform electric field? So we imagine an electric field, and this represents the direction of increasing field. This would be the direction of net force. This would be the direction of the dipole moment. So dipole moment, electric field and force all acting in the same direction. So the positive charge would experience a force in the direction of field. Negative charge would be experiencing a force opposite to the direction of electric field. The electric field is increasing in this direction, so E at this point would be greater. That means if I call this as point A, I call this as the point B, then electric field at point B would be greater than electric field at A, and that is why the net force would be in this direction. So here the direction of the dipole moment is parallel to E. Dipole has net force in the direction of increasing field, and net torque is equal to 0. What is the second option here? Here P is anti-parallel to E. This is the direction of increasing field. Now the direction of dipole moment opposite to the direction of field. This negative charge would be experiencing a force opposite to the direction of field, and positive charge would be experiencing a force in the direction of field. If this is A and this is B, then once again the electric field at B would be greater than electric field at A. So net force would be in this direction. So the direction of the net force has changed. So net torque on the dipole is 0. The dipole experiences a net force in the direction of decreasing electric field, that is to the left. Now, what does the force depend on? It depends upon the orientation of the dipole moment P with respect to E. I hope you very well understand how will the dipole now behave in uniform as well as non-uniform electric field. That's all in this lecture of the day. Thank you very much. Hope you enjoyed electrostatics. At last, once again, I request you just to like and subscribe my channel. Press bell icon button so that you receive the next video lecture notification in time. Thank you.